And that means today and Thursday we'll cover chapter 9. And I've got a break scheduled in the slide, so I won't make the mistake and go over. And then we'll have a Thanksgiving break next week, which means you'll have all that time to ignore chemistry before you come back for a review. And we'll have, that's a Tuesday, and then the following Thursday, we'll have an exam on this material. The final exam is another issue. There are a few of you that are going into the buffer, and that means check that problem. Ah, there it goes. Okay. Let's just hope it holds until we finish today. Where was that? Final exam. So some of you have a pretty substantial buffer for a grade of A. If you don't mess that up on this last exam, then I'm contemplating, for those who have A's, contemplating canceling the final exam. And then if you have a B or less, then the final exam is your opportunity to catch up. So I think I was correct. The final exam is worth 2 exams, 2 exam grades. So if you've got a C or a B and you want to boost your grade, then the final exam would be a good place to do it. But if you've already got an A, then I think you mastered the material well enough that you can dispense with the final exam. And that's my position right now. I don't think that'll change. And it'll relieve some of you of headaches on exam day. But I'd like to wait till after this exam to make that decision, this upcoming exam, because you need to master all the material to be exempt from the final. And if you do well on the next exam, then I think I'm leaning toward that. Well, just show up for the class. Yeah, and then we can find out. If you made a printout, a copy of the PowerPoints before about 10 or 10:30 this morning, you'll notice they will have changed. Not major changes, but some added information. So I'll just call your attention to that. The review document that I'm using, I've broken the review into 2 documents, and the one I'm distributing today is version 1. Looks like that. Okay, but when we do the review, when we get back from Thanksgiving break, I'm going to take problems from both version 1 and version 2. Because I think they're different enough that they'd be worth looking at separately. So if you want to, you can go into Brightspace and take a look at version 2 also. But I felt that version 1 was the only one I could get away with printing. If I try to print version 2, it'll just, like I said before, I've broken the printer by printing too much, and I don't want to do that again. Okay, chapter 9. Now, let me see if this thing is going to work. Been giving me trouble lately. Ah, that's good. Put the pointer up there in the corner. All right. So in this chapter, we're going to pick up where we left off in chapter 8 with the VSEPR model. We're still in the localized electron model of the valence bond theory, valence bond theory, localized electron model, and then the VSEPR model goes with that. And we're going to spend today finishing up on that type of material, where the electrons are considered to be owned by each atom and simply shared for bonding. Then we'll come back on Thursday and finish off with molecular orbital theory, which takes the electrons and makes them now the property of the molecule rather than the property of individual atoms. So that's where we're headed. Okay, so if we draw the Lewis structure for methane, here's our example. It's going to present a problem with the valence bond theory and the localized electron model. The shape of the methane molecule, according to what we know up to this point, is a tetrahedron. Right? If we draw the Lewis dot structure, there are no dots, of course, because there are no unbonded electrons. But then if we put it in a geometric shape, like that, then we have hydrogens at the four corners. So that's the shape that we predict from the VSEPR model. And the bond angle should be 109.5 degrees. Okay. Here's the problem. If the localized electron model is true, then this carbon atom has a valence shell with 2 electrons in the S and 2 electrons in the P. Okay. If the localized electron model is true, then these P's will give you a different type of bond than these S's will. And this symmetry would not be possible. I think that's right. Yeah, 6. We've got a 1s2 over here that's not valence, right? So we're only concerned with these two. So if the s orbitals, see the s orbitals are spherical shape, they're going to give a different type of bond. In fact, they can be bonded anywhere. Whereas the p orbitals are those dumbbell shape. They're pointing to the XYZ axis, right? Like that, like that, like that, like that, like that, like that. So they would give a certain type of bond directed at actually what we would expect to get out of this. But then the s orbitals could be anywhere, right? So a regular shape like this doesn't fit with the localized electron model. All right, so here's where we decide. Are we going to throw the model out, throw that theory out? Are we going to restrict its use, or are we going to modify it? And the choice in this case is to modify it. And the reason we're doing that is because the experimental data says that this is the true shape of that molecule. It does have a tetrahedral, a regular arrangement, even though we start off with this disparity in orbital shapes. So what we have to do is decide how we're going to get around that. And the method that's chosen is called hybridization, where we actually mix these orbitals and we come out with a new set of orbitals that are regular and give us the shape we want. Linus Pauling is responsible for proposing this method of hybridization in the early 30s. And he actually proposed it for very simple molecules, but it's been expanded to more complex molecules with some modifications. All right, so I've already said that. All right, so these 4 equivalent orbitals now are a mix, and they still belong to carbon. And then the hydrogens overlap their s orbitals with these new carbon orbitals. And what we call them is based upon where they came from. They're called sp3 hybrids. Oops. Notice that we had 2 electrons here and 2 electrons here in the p, 2 in the s and 2 in the p. Now we have those possible positions. Now we have also 4 positions. So we preserve the number of places for electrons with the hybrid orbital. Right? We don't create orbitals, we don't destroy them, we just modify them. We hybridize them. Now, all of this is still based upon probability. We're still using quantum mechanical formulas that are solved in different ways to give you this. This is what we work with because we're not mathematical geniuses, at least I'm not. So we take their word for it, and the solution to these quantum mechanical equations give us these hybrids rather than the individual S's and P's. Okay, so we combine 1s and 3p orbitals. Oh, by the way, this s is 1, and remember you can have 1 orbital here, you can have 3 there. Right? So we take those 3 and that 1. Even though this one originally only has 2 there, and this one has 2 here. But we have 3 orbitals here and 1 there, which gives us S and P, 3 P's. That's so we can have room for each one of these. In other words, now this one has an electron from each one of these here from the carbon, and then the hydrogens have an electron from each one of them. And that makes your 2 electrons for a bond. All right, so when we hybridize these orbitals, what happens to the energy level? Well, that's the thing about the valence bond theory. It's not designed, and it never has been very good at predicting actual numerical values for energies. We can look at them relative to one another, and we see that the energy level for the P's are going to be higher than the S's. Well, we already know that. But then the sp3s, when they hybridize, they're somewhere in between, which kind of makes sense. We just don't know exactly where. Let's see, I was supposed to have a oh. Sorry for bouncing around like that. But I modified the slide set, and I must have got hold of the wrong one. Okay. Brightspace has the modified one. And I don't know if I want to take time to load up the other one or not. I should, but let's move ahead. That'll eat up too much of our time. Notice that the location of this level, energy level for the sp3 hybrids, not only is it between here, but it's shifted decidedly higher toward the P's. And this is like our weighted average problem, right? you've got 3 of these at this energy level, and only 1 at that energy level. So naturally, it's going to be at a higher level. It's going to be very close to the P's. We just don't know exactly where. All right, now our model, our equations, and the probabilities they predict for shapes of orbitals and location of electron is still not exact. Right? We try to go for energies where we can, and leave the positions to kind of a region or the Heisenberg uncertainty principle. Remember, we kind of favor energies, and we leave the location of the electrons to a probability. So this is the probability distribution calculated for each of the hybridized orbitals. Right? Notice that they're all pointing to points of an equilateral triangle. Excuse me, a tetrahedron. There's a bigger picture with the hydrogens attached. Now, this particular this modification to the localized electron model satisfies. I mean, it predicts exactly the shape that you're going to see in this molecule. How would it work with ammonia, though? We know ammonia has a lone pair up there, and hydrogens here and hydrogens here, and then 1 in the back. So it has the tetrahedral shape, right? But it only has 3 atoms and a lone pair, right? So does that fit the model? Well, we would expect it to be, based upon our VSEPR model, in the Lewis dot structure, to give us a tetrahedral electronic configuration. And how would that fit with the hybridized orbitals? It fits perfectly. You take the 2s orbitals and the 2p orbitals, which nitrogen does have, right? It's next door neighbor to carbon. So it does have this 2s and this 2p with its 3 orbitals. So you hybridize it to an sp3 hybrid. That gives you 4 positions. Well, you use 3 of them here, and the 4th one holds that lone pair. And there's our model. The lone pair resides in this sp3 orbital. And you still get a tetrahedral arrangement of electrons in the bonding or non-bonding electrons. But of course, it still holds that the bond angles are going to be somewhat less than 109.5, because this lone pair is not bonded to any, it's not restricted by the presence of another atom. So they tend to balloon out, and they put pressure. They put pressure on these bonds and atoms and squeeze them down. So the bond angle actually is less than 109.5. Okay, how about a little more complicated molecule? C2H4 is called ethylene. Right? If we draw the Lewis dot structure, which is where you would begin with a localized electron model, this has 2 times 4 is 8, and then 4 more, so we have 12 electrons. Right? Carbon, 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 4 hydrogens. Okay, so 2, 4, 6, 8, 10, and that gives us 2 electrons left over. They have to go here. Okay. But we need an octet, right? So we put that one over there, and now we've got a double bond. So what does the VSEPR say about the symmetry around that central atom? 1, 2, 3 groups, right? 3 groups equals trigonal planar. Okay, with 120-degree bond angle. Okay, and this one's going to be exactly the same. So how do you hybridize to get that? Well, SP3 won't do it because it's the wrong bond angle and it's got too many groups required. So instead, we hybridize. Right, if we have an S here and 3 P's there, instead of hybridizing all 4 of them, we only hybridize 2 P's and leave this one alone. So now we have an sp2 hybrid plus an unused P. Okay, and this unused P orbital is perpendicular to this plane, right? These 3 are going to be in a plane. Well, the unused P is going to be perpendicular to them. So sp2 will give us trigonal planar. Okay. Okay, just what I said, sp3 won't work. So we have an sp2 hybridization that gives you the trigonal planar. And 1 p orbital is not used. Okay, the comment that's missing here is that, remember when we first started using VSEPR, I was complaining about the name, the valence, let's see, valence shell electron pair repulsion. Electron pair, that's the part that I was ragging on. Well, actually, that's true. Because notice here, this symmetry is trigonal planar. And it's as if that extra bond didn't exist, right? These 3 are actually part of that hybridized orbital, and this P is used to make that double bond. So in one respect, that's true. Valence shell electron pair repulsion. And that brings us to the discussion of what types of bonds do we have here. If the bond is on axis between the atoms, it's called a sigma bond. We use a small Greek letter, their S, sigma. And those pairs are shared between the atoms. So there you go, between those 2 carbons, and actually between the carbons and the hydrogens. These are all sigmas, because they're on the axis between the atoms. And these are the ones that are part of the hybridized orbital overlap, if there is one. Of course, that one's not hybridized, but these 3 that are contributed by that carbon are hybridized orbitals. The pi bonds are formed off axis. In other words, you got this unused P here and here, and there's overlap between them, and they're off axis. That second, that double bond is a pi bond. And the pi bonds are usually not as strong as the sigmas. I think I can say that fairly certain. Because you have some, it's like trying to shoot a gun around a corner, right? You're not going to be too successful at it unless you have a curved barrel. Or that special gun that was developed by the Israelis. I forget what they call it. Anyway, the pi bonds are not as strong as the sigmas. That's why when we said earlier, when we're talking about bond strength, a single bond has a certain strength, and then a single plus a double is stronger, but it's not as strong as double of the sigma, right? It's not as strong as doubles of the single bond because the first pi bond is weaker. That's why it's not linear. It's not a linear progression in strength, bond strength. Right? And you can't have a double bond without first having a single sigma bond. So all pi bonds come after single bonds. Now we can have a third one, right? If we have nitrogen, nitrogen actually has 3. So that means it has some unused P's that are going this way, and then there are P's out of the board that are doing overlap. So you get 2 pi bonds here. You get a sigma there, and you get a pi here and a pi here. Okay, so this illustrates the unused 2p orbital, and then the hybridized sp2 orbitals. There are only 3 of them. Notice this 1s and 2 p's means 3 hybrid orbitals. That's pretty simple math. There's the unused p that goes into the pi bonds. And this is what the probability map looks like. And this is sort of an artist rendition of the overlap of these unused p's. Okay, how about carbon dioxide? What would it look like? Well, we've drawn carbon dioxide before, haven't we? Just like that. So if we're concerned here with having a linear arrangement, right? And that's what carbon dioxide would be at 180 degrees. Right? A linear means you only need 2 hybridized orbitals to connect with these oxygens. So we would just hybridize 1s and 1p. And that's for the carbon. The oxygen is a separate matter. For the carbon is sp. I probably should put it over the carbon. So the carbon is sp hybridized. And that gives you room for a bond this way and a bond that way. And then you have 2 unused p's. One of the unused p's goes into a pi bond here, and the other one goes into a pi bond here. So you have a sigma, and a pi on either side. Right. This is just derived from what we know of the VSEPR model, and then we go to hybridization, sp hybridization. If it's linear, you have sp. So what we're finding is that if we know what the geometry is, we can predict the hybridization. Right. Up to this point, the 4 groups, right? We have groups like this. 4 groups gives us tetrahedral and sp3 hybridization. 3 groups gives us trigonal planar and sp2 hybridization. 2 groups, one on either side, gives us linear and sp hybridization. Now this is electronic configuration, because you may not have all these positions filled with atoms. You may have to put lone pairs in there. But for simplicity's sake, and not to confuse you too much in the beginning, we're using molecules that, well, except for nitrogen, trying to use molecules that have atoms occupying those places. All right, so there you have 2 unused p orbitals and 2 hybridized sps. And these are the ones that are used for the pi bonding. And that seems to be the pattern. If you're going to get a pi bond, you've got to have an unused atomic orbital. And the sigmas are created by hybridization. All right. So there you go. This just shows that this one here, hybridize is on this plane, kind of inside, in and out of the board. And this one is along the plane of the board. Now, I mentioned this was hybridization for carbon. How about oxygens? Well, oxygen has 1, 2, 3 groups, so it would be sp2 hybridized. And you would have one sp being used for the sigma bond with this sp over here. And then these would be, these lone pairs would occupy the other two sp2 hybrids on each side. And that's what we're trying to show here. These are all hybridized orbitals for oxygen. And these two have lone pairs in them. These two have lone pairs. And this one on either side forms a sigma bond with the sp from carbon. All right, I already drew this one on the board. That's the Lewis dot structure. We know that already. Each nitrogen has 2 effective pairs, right? One on this side and one on that side. So it should be an sp hybridized nitrogen. Okay. And one side of the sp hybrid bonds with the other nitrogen. And then the unused one has a lone pair in it. Then the other 2 unused 2p's would form the pi bonds, 2 of them actually. All right. So this is an artist's rendition. What it would look like. All right, how about PCl5? Oops, you need to erase that. Here we go. PCl5, if we use what we know of the VSEPR model, this would be phosphorus is 5, and 5 times 7 is 35, so we have 40 electrons. Right. Phosphorus here, 1, 2, 3, 4, 5. Like that. There. So we have 2, 4, 6, 2, 4, 6, 8, 10. 30 electrons left. So if we put 6 around each one of these 5, that uses up all the 30s. All right. So what's the geometry that we get out of this? If you've got 5 groups, you should have a trigonal bipyramid. So this, and then phosphorus in the middle, chlorine here, 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 and here. Draw my CLs better. 1, 2, 3, 4, 5. Okay, so you have a trigonal bipyramid. Right? How do you get a hybridized orbital out of that? Well, we've used up all of our S's and P's. Right? So where are we headed? The only place to go is D's. So notice that phosphorus is located in the third period, which means its principal number, quantum number is 3. That means it has access to S, P, and D. So we use a d orbital out of p, and that means for 5 groups, we have a trigonal bipyramid, and we use a d, s, p, 3. Now don't ask me why d comes first. Right? You would think that low energy, next energy, next energy, it should be sp3d, but no, they say dsp3. I don't know who decided it, but I've never seen it any other way, so we'll have to call it that. All right, and the bond angles are going to be what? Well, let's see. A bond angle between here and here is 120 degrees. Right? A bond angle between one of these and one of these is a right angle. And a bond angle between this one and this one is 180 degrees. So you've got 3 different bond angles here. 180, 120, and 90 degrees possible. All right. You're not going to find a DSP3 hybridization with anything in the second period. So oxygen, nitrogen, fluorine, boron, none of those will DSP3 hybridize. You have to get into the third period before you have access to that D. Because hybridizations are not going to occur with orbitals that are of different energy levels, right? They're not going to hybridize from a third level energy level to a fourth level or a second to a third. They're always in their own energy level. So at least we're consistent with that. And originally Bohr said that N represents energy level. And that translated further into the quantum mechanics. Okay, what we got left? We got 6 groups left, right? That's going to be an octahedron. So take a wild guess and say, what kind of hybridization will we get there? D2sp3. That gives you 6. 1, 2, 3, 4, 5, 6. So what's our example? Xenon tetrafluoride. So in this case, we are going to have some lone pairs, right? Xenon tetrafluoride. We remember, wasn't that one of the exam questions? Xenon, maybe not. Maybe I'm thinking of PowerPoint slides. So this would be 4 times 7 is 28, and 8 is 36. So we have xenon, and then we have fluorine. So 2, 4, 6, 8 is 28. And then if we do like this, and put 6 more around each fluorine, that's 4 times 6 is 20, is 24. So 4 electrons means a pair here and a pair here. Right? So now we have 1, 2, 3, 4, 5, 6. That means overall, we have xenon in the middle and we have fluorines around the square. And then we have lone pair here and a lone pair there. So these 2 lone pairs occupy one of those, or actually 2 of those, D2sp3 hybrids. Okay, and the bond angles are going to be here, 90 degrees or 180. It's the only possibility. All right. So there you have it. That's as far as we're going to go. Like we did with the VSEPR, we stopped at 6. And we're going to do that for the hybridized orbitals also. Well, it's a little bit of evidence. We know that the hybridization can't be sp3, right? Methane had 4 hydrogens. Xenon is attached to 4 fluorines, right? So why is it not sp3 hybridized? Because we only need, we only need 4 positions. Well, the evidence is that this molecule is square planar. Right? So that rules out sp3. sp3 can't be square planar; it has to be tetrahedral. So the lone pairs have to be included in the hybridizing model. All right, so that's what it looks like if you let an artist let their imagination go. Let's see. Let me see how much farther we go to the break. Got that one, we got that one. Do we have time to tear this one apart? Okay. Erase this. I'm going to leave that other part up there. Okay, so the question is, what's the structure and what's the hybridization for hydrogen cyanide? Right. We've already drawn this one before. Right, Lewis dot structure there, and like that. That's the Lewis dot structure for hydrogen cyanide. Well, carbon has two groups, which means it would be linear or sp hybridized. Nitrogen has one from this side and one from the lone pair. It's also sp hybridized. Hydrogen doesn't have to hybridize. It's only got one s orbital, and that's all it needs. So both of them are sp hybridized. We have a sigma bond here, we have a sigma bond here, and we have two pi bonds. Oops. Didn't mean to put a hashtag up there. There we go. So there's a sigma, there's another sigma, and there are your two pi's. Okay. Let's see. I think we got time to do this one. Each one of these. Determine the bond angle and expected hybridization of the central atom for each of the following molecules. We've already done ammonia. Right. Ammonia hybridization is going to be like methane. It's going to be sp3 hybridized, and the bond angle nominally is 109.5 degrees. Let's go ahead and do CO2. We did that one, and that's sp hybridization because it's linear. And the bond angle is 180 degrees. Right, so we don't have to redo those. How about SO2? Okay, SO2, we have to draw the Lewis dot structure first. So sulfur is 6, oxygen is 6, that's 12, 2 times 6 is 12, 18. So 18 electrons means this, there, 2, 4, and that's 14 electrons. So 6 more around each oxygen is minus 12, so we have 2. Okay, does it just say around the central atom? Yes, we're only concerned with the central atom stuff. So we have 3 groups around here, which means it's trigonal planar. Trigonal planar means sp2 hybridized. And the bonds will be, the bond angle should be 120 degrees. Okay, ICL5. Okay. So we have 6 halogens would be 42 electrons. So we have iodine in the middle. We have chlorine, 2, 4, 6, 8, 10 is 32 electrons. So 6 more times 5 is 30. And we have 2 electrons that have to go here. Okay, so that means 6 groups octahedral. We have an octahedral shape, that's D2sp3 hybridized. And the bond angles are going to be 90 degrees or 180 degrees. Did I lose anybody? Okay. Let's see. The last one. Krypton difluoride. So we have 8 for krypton, it's a noble gas, and then 2 times 7 is 14. Let's see, 14 and 8 is 22. Okay, krypton, fluorine, 2, 4 is 6, 8, 18 electrons. So that's 6 times 2 is 12. And that's 6 electrons left over. 4, 6. So we have 1, 2, 3, 4, 5. So this is trigonal bipyramid. And a trigonal bipyramid has DSP3 hybridization. And the trigonal bipyramid is the one that has a whole bunch of angles. Let's see, it could be 90. It could be 120. Oh, excuse me. No, that's not correct. When you're talking about bond angles, you got to have atoms. So where are the atoms located? Right. If we have three lone pairs, and they're all around the krypton in the plane. And the fluorines are going to be at the apexes. So there's only one bond angle possible. 180 degrees. Let's see. Yep. All right, let's see if the animation confirms. 1095 SP3, SO2, 120 degrees SP2, 180. Didn't say anything about polarity. I must have stuck that in there. That's a freebie. CO2 is 180, yes, SP hybridized, and ICL3 is T2SP3. 90 degrees. So 180 in there. Oh, I've erased it already. Did we have lone pair in here? We had lone pair. Okay, that's why it's not 90 degrees. Because the location of the, that's why it's not 180. Because the location of the lone pair was in a position that didn't allow for 180 degree bond angle. All right, so we're coming down the wire on this one. So when we're using the localized electron model and then proceeding into the hybridization fixed, you always have to draw the Lewis dot structure. You determine the arrangement of electron pairs using the VSEPR model. And then you know the number of effective pairs, which is we're calling groups. And that will tell you what the hybridization is. Right? If it's 4 groups, then you need 4 hybrid orbitals. If it's 3 groups, you need 3 hybrid orbitals. If it's 2, you need 2. It's 5, you need 5 DSP3. If it's 6, you need D2SP3. Gives you 6 hybrid orbitals. And then you proceed from there to determine what the molecular structure is, if that's the question. Okay, limitations. Same as always. The localized electron model assumes that all the electrons belong to individual atoms. They're localized on the atoms. That's why we had to introduce the concept of resonance. When we have 2 or more equivalent Lewis dot structures. I should say not equivalent, but valid. They're valid Lewis dot structures. Then we have to resonate them in order to explain the reality, what the measurements say. Localized electron model doesn't deal effectively with molecules that contain unpaired electrons. Unpaired electrons are, my mind's gone blank. Free radicals. It really doesn't know what to do with them, right? Because it's not a pair; it's just one electron. And we had we had one example like that, I believe, that came up in the PowerPoint slide set in chapter 8. And then lastly, the localized electron model, and in fact, the valence bond theory has not, it doesn't provide direct information about bond energies. It doesn't predict bond energies. Now, we're not going to go into a lot of detail when we get to the molecular orbital model about energies, except to say they're relative to one another. But that's the improvement that we're going to derive from the molecular orbital model, is that it is able to mathematically predict energies, whereas this model does not. And I think the reason that we're driving a stake through the heart of a localized electron model is so that the molecular orbital model will have some traction once it's introduced. Okay, we're finished a little early.